Oh, testing. Yeah. Morning, everyone. The last class. So maybe we discuss what's left with last lecture first, and then I'll talk about one question in the assignment. Okay. So where did we stop last time? So last time we have an idempotent. A ring. Okay, what's the use of this idempotent? Idempotent means what? Uh, idempotent means what? E. E will square to itself. Okay. E squared to E. Okay. So what's the use of this idempotent? We can use it to split the ring. Okay, we can split the ring into E R cross 1 minus E R. Okay. E is an idempotent. 1 minus E is also an idempotent. Okay, you can try and expand 1 minus E squared, and you will get 1 minus E. Okay, what's this isomorphism here? I send all the R to E times R, comma 1 minus E times R. Okay, just multiplication map. And then we show that this multiplication map define a homomorphism. Okay, let's call this map phi. And we have shown that the multiplication by E the phi map is a ring homomorphism. If not, you should try and write out again. If you try and write it out, why is it a ring homomorphism? I guess the non-obvious one is send phi identity to identity in this ring. You need to know what's the identity inside this product ring. Okay, what's the identity in this product ring? What's the multiplicative identity here? Hmm? 1? 1? Is it 1? But 1 is not in the ring. I'm not being in the ring. Huh? Why? So R contains 1 right? But idempotent times 1, you get E. Unless your idempotent is invertible. 1 is contained in the R. Okay, but there's an obvious identity in both of these rings, which is E and 1 minus E. Because E is an idempotent, E little r multiplied by E always give you a E little r. Okay, so E act as an identity in ER. Similarly for E minus 1 minus E times R. Because 1 minus E is another idempotent. I have provided this proof in the previous lecture notes, where you can check. I provide the proof inside the lecture notes that I posted out yesterday. is in lecture 27. So it's in lecture 27. Yeah. So the kernel of this is this multiplicative identity 10 here. This one, not this one. This is the 10 TD. Yeah, here. With the LLC obtained by restriction from X, the principal ideal EX is a ring with identity E. Again, the idempotent is the identity element. And I provide the proof here. You can check. Okay. Yeah. Okay, so we show that this is the ring homomorphism. To show this is an isomorphism, unique, injective, and surjectivity. Okay, last time we briefly talked about surjectivity. So we need to take a UV okay, in ER cross 1 minus ER. Then we can write UV equals to E times liter R1 and 1 minus times liter R2 for some R1, R2. Yeah. Okay. So that's the definition of ER and 1 minus ER. Okay. And then we want to show that we want to find what's the pre-image of this UV. So last time I suggest you to try U plus V. Okay, I claim that U plus V is the image of UV. Okay, so let's try it out. So where should the U plus V go under V? Where should the U plus V go under V? E times U plus V, comma 1 minus E times U plus V. Okay, but you do anything here? You can't quite do anything. But we have UV in terms of E, right? So we have to substitute it in. So U becomes what? ER1 plus V is 1 minus E times R2, right? And then what? 1 minus E times ER1 plus 1 minus E times R2. Okay or not? Okay. 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 So next, what's next? EE, so you expand it using distributivity, right? Okay, E times ER1, you should get ER1 again. But E times 1 minus E, what do you get? Still remember what do you get when you multiply E and E minus E together? 1 minus E. And you get E minus E squared. But E is an identity. So you get 0. So when E and 1 minus E, they multiply, they get 0. Okay, so the R2 term get killed in the first one. Okay. Similarly, on the other side, because you're multiplied by 1 minus E, so the 1 minus E part survives. Okay, and then the R1 term get killed because 1 minus E times E. Okay, so altogether you will get ER1 and minus 1 minus ER2, which is U and V. Okay, does it make sense? Yeah. Okay. Okay. Next, we need to show phi is surjective. Okay, next part we need to show phi is injective. So what is the definition of phi being injective? Huh? What's the definition of phi being injective? Huh? Sorry? Different input get different output. Or in other words, what? If phi x equals to phi y, then you need to show that x equals to y. Okay? Right. So suppose px equals to phi y. Okay? Meaning what? Meaning ex comma 1 minus ex equals to ey comma 1 minus ey. Okay? But so you want to show that x equals to 1. Okay, how you gonna use this piece of information to show x equals to 1? Yeah, let you think about it for 2 minutes. Okay, any idea? Sorry, ex equals to ey, sure. Ex equals to ey, and then 1 minus ex equals to 1 minus ey. Okay, how are you going to use this information to show x equals to 1? Sorry? Okay, so you can write that x is equals to ex. Okay, so x, what is x for, first of all? X is identity times x. Okay, so how do you create idempotent here? You can add an idempotent and take away an idempotent. Okay, then you can do distributivity here. E times x plus 1 minus e x. Okay, because addition here is commutative. Okay, so I can commute and then I do distributivity. Okay, but like uh, like Zhen saying ex equals to ey. Okay, so we can replace the first term with ey, replace the second term with 1 minus ey, and then do the same trick. You will get y. Okay, so meaning what? An idempotent plus uh, the 1 minus the idempotent is equal to 1. Or we can see that actually these two are orthogonal to each other. They are somehow orthogonal. Okay. Okay. No. Okay. So what I want to say is there's some orthogonality here. because we split 1 into E plus 1 minus E. Okay? And then when you dot them together, when you multiply them together, you get 0. Okay, there's some orthogonality inside here. Okay, well, I'm trying to link this algebra back to geometry. Okay. later, later I'll let you see another example about these how these ideals connect back to geometry. Okay. All right. So next, so how to use this example here? For example, Z6. Can you find an idempotent inside this Z6? You try and find one. What's the idempotent inside Z6? 1. 1 is not very interesting, right? 1, if you take 1, so just now I want to split into E and 1 minus E. So if you take 1, you split into 1 and 0. So it's just itself kind of 0 ring. So almost it's the same as the original ring because you just attach a 0 beside it. Okay, so which one is a non-trivial idempotent? 3, right? 3 is a non-trivial idempotent here. 3 is what? 3 square equals to 9. But 9 is equal to 3 more 6. Okay, so 3 square to 3 in mod 6. Okay, so we can use the proposition just now. I can split Z6 into 3 Z mod 6 times 1 minus 3 Z mod 6. Okay, so what on earth is this? Okay, what on earth is this? What is 1 mod 3 or minus 3 in Z6? What is 1 minus 3 in Z6? 4. Okay. So what does 3 times Z6 means? What does 4 times Z6 mean? I multiply. So in Z3, Z6, I multiply everything in Z6 by 3. In Z6, 4Z6, I multiply everything in 4. Okay, so let's see what happened here. So in the first case, I have 0, 3, 6, 12, 15, 18, right? Okay. But remember, we are living in mod 6. Okay. The other side, what do I have? I have 0 again, because 0 is in every Z mod n Z. And then I have 1. 1 times 4, I get 4. 2 times 4, I get 8. 3 times 4, I get 12. Okay. 4 times 4, I get 16. And so on. 24. Okay. I think we can stop here. And then mod 6 again. Right. Similarly, I can get rid of 18 also because there's only 5 or 6. Yeah. Okay, I think we should have 6. Okay, correct. Okay, but what is this? What is this? Here, after mod 6, who survived? There's 3 and 0. Here, mod 6, how many things survive? How many things survive on the right hand side? 0, 4, and 2. Okay, so what are these things actually? There's really only one group or one ring with 2 elements, right? Don't review one. This is Z2. And then this one is cyclic. Okay, so this is Z3. So you get what? You get Z2 cross Z3. I think we also have shown this in a group sense. This is in a ring sense. Okay, so this isomorphism respect ring structure. Okay, not just group, not just addition, also multiplication. Okay, so this one is stronger. Last time we only talked about group, right? We can split any finitely generated abelian group, okay, into products of Zn or Z and Z. Okay, but here is a ring isomorphism. Okay, so whenever you write this isomorphism, right, you need to ask yourself, this one is a group isomorphism, ring isomorphism, or vector space isomorphism we have learned before. Okay, no? Okay, so 3Z6 is actually Z2. 4Z6 actually Z3. Okay. Any question up to here? Yes. 18. So let me check. So initially you got 0, 1, 2, 3, 4, 5, 6, right? So every number you multiply by 3. Huh? What? Hey, sorry. 1, 2, 3, 4, 5, 6. Hey, what am I doing? 0, 1, 2, 3, 4, 5. Okay, no more 6, right? 6 is 0. Okay, times 3, times 3, times 3, times 3, times 3, times 3. Okay, shouldn't be 18, should be 9. You can put of course you can put 18 in because 18 is just 0. It's the same concept with 0, so it's but we should have 9. Yeah. Okay. Yeah. Any other question? Any other question? Yeah. Okay. Okay about this part. Okay. So yeah. Why is it equal to mod 2 times mod 3? So you if to be precise, you should create the isomorphism here. So you need to create isomorphism. So for example, 0 you should send to 0 in Z2, 3 you should send to 1 in Z2. Isomorphism. Okay, let me write down. So you create for example, a surjective homomorphism like this. Okay, 0 to 0, 3 or 2, should be 3. 3 to 1. Okay, and then the kernel of this V should be mod 6. Okay, then by first isomorphism theorem, this free ring, what to call it, or either ideal, modeled by 6 should be isomorphic to Z2. Like this. Okay. Yeah. Okay. Yeah. It will be easy to see why this kernel is 0 because 1 plus 1 on Z2 is 0. So meaning 3 plus 3 should be in the kernel. 3 plus 3 is 6. Okay. Okay. Yeah. Okay. Similarly for Z3, you should create this map. This map here. Okay. So you can easily guess that 0 should send to 0 in the Z3, 2 should send to the 1 in Z3, and then 4 should send to the 2 in Z3. Okay, and then see that the kernel is generated by this 6. Okay, okay. Okay, so maybe let's go back to one assignment question. So last time we have a impromptu meeting with some of you. This one example, maybe I can show you a little bit. So the let me show you. I updated the assignment a bit. Okay, one of them is a slight typo here. So there's no F before, should be an F. X0 should go to F00, not 00. If 00, then everything is in the kernel. Okay, yeah. And then this 2C here, I have made a typo. I don't put a square there. So if you choose to do the textbook question, you can try this out. If not, you also can do back the original question. Okay, both will get answer using the method. Different answer, I mean, yeah, using the method measure. Or if you bold enough, you can do both. Okay, yeah, you do either one, I will give you mark. Okay, no extra mark. Okay, okay, yeah. So last time we have some discussion on this. I discussed with Y, and then Karen contribute a bit. So what is this actually? S to T, Y to T squared, Z to T cubed. Is this familiar or not? Let me remind you a bit. Xt equals to T, Yt equals to T squared, Zt equals to T cubed. What's this? Last year in this time, you learned. What's this? Yeah, the parametric equation. This is what I'm teaching in the other class. What is this? Let's say this thing, all of them live in R. T live in R. X, Y, Z also live in R. So this, what object is this? What object is this? Let me fix T in some domain. What's this? What's this object? What's this object? A curve, space curve. Okay, what's this space curve here? So if you just look at X and Y, right, it is like this. Okay, but it lift up in Z. Okay, so it have to increase in height. So maybe do something like this. Space curve. Okay. 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 So this is actually a space curve. If you sub your T, X, Y, Z, T in the right position. So that's why we say this thing is formal. Because if we put in R, we will get this space curve. If I put in different number field, okay, maybe I put complex number, I put F2, F3, Z, so on, it will give me different objective. So that's why this algebra becomes abstract. We can apply in different spaces. I can apply analysis, I can apply geometry. Okay. Okay, so last time what's the problem? So this problem says that we want to find the kernel. Okay, so what's in this kernel here? What is it in this kernel here? What's the kernel of this map? V. Okay, V going from X, Y, Z to T. Okay, what's this kernel here? This kernel here is what? If a lot of you, I think you will try all the possible combination. For example, you will try x cubed minus z. Okay, you will try x cubed minus y, and then you will try probably x cubed minus z squared. Okay, but if you try to go through the division with remainder, what you really need actually just two of them, either two of them. Okay, two of them is enough. Okay, meaning one you can write as a linear combination as the other two. Okay, right. Okay. In fact, uh, in fact, uh, we have done this yesterday. I stuck for quite long. Instead, you can done this. So you can go and check y cubed minus z squared. Actually, you can write as a linear combination of s cubed minus z and did I do something wrong? Yeah, x squared minus 1. Okay, you can try. It's pretty hard. Okay, you can get 1y times x squared minus y squared minus zx plus 2y squared times x squared minus y plus z plus xy times x cubed minus z. Okay, maybe you will ask me how you get this linear combination. Want to square again, and then something before the coefficient is so complicated. Right, how to get this? Actually, I don't immediately get this. So first, I don't provided this. He write minus z squared plus zxy equal to some linear combination of x cubed minus z and s squared minus 1. But this guy here is close to what we want. What do we want? We want y cubed minus z squared. But here we have zxy. So what's the difference? If I manage to show that zx and y squared is in the same concept, then I can transform this into y cubed. Then this is what I do. I show that zx minus y squared is some linear combination of x cubed minus z and x squared minus y. Okay. Okay. Yeah. So so you need to learn how to break the problems down to easier problems. Okay. So you break the degree 3 into degree 2 equation to solve. Okay, only then you get the long answer I have just now. Okay, only then you will get this long answer you get. So you break down the question. Okay, don't straight away just solve this guy. It's too hard. If you want to straight away solve it, there you go. Please come up with this long linear combination. If you can, you can, but most probably you can't. So you break down into few steps. Okay, now. And then you combine steps. Then this is what we do in mathematics. Okay, it's not that I straight away tell you a whole way, a complete way to solve a question. Not like that. You can do this before because it's easy. Okay, but always you need to break the problems down. Okay or not? Okay. So meaning I can actually get rid of this generator inside my ideal. Okay. Okay, so what does this kernel do now? Okay, what does this kernel represent? Actually, it's x cubed minus z trace out a surface. You know what surface is this? S cubed minus z. Sorry? Sorry? Z equals to x cubed. So let's get z equals to x cubed first. So z equals to x cubed Z equals to S cubed. So A should be something like this. Z equals to S cubed. But this is a surface in 3 dimension. Right? If I add another axis, okay, Y, this means what? I have all these lines together. How should I draw this better? Or maybe I should point it in this way. Okay, then it will be easier to draw like this. Okay, this is my surface. You join them together. Okay, makes sense? Okay, Z equals to X cubed. The other one, Y equals to X squared. Okay, what's this surface here? Y equals to X squared. So where's my Y? So I'm better to draw the same orientation. Easier to see. So here is X, here is Y, here is Z. Y equals to X squared. Meaning what? You have Y equals to X squared, something like this. So you have some shape like this. Y equals to X squared. Correct? On the XY plane. So that's regardless of Z, right? So you have increasing, not increasing, I mean, it extend in the Z direction. Imagine or not? So let me show you. Right. So you have X squared like this. So it extend like this. Can see or not? Okay. So you have these pieces, and then together with the pieces before, these pieces here. Let me show you. So maybe S cube, something look like this. Right. So you have these two pieces intersect together. Intersection of two surfaces give you a line. Okay. So this is the space curve it gives you. This curve lies in the intersection of these two planes. That's why you kill these two polynomial inside your kernel. Okay. So this is the connection between algebra and geometry. Okay, we study the geometry using ideal. Okay, using algebra. So if you're gonna learn more, this is in the algebraic geometry. Okay, we study geometry using ideal. And this is phrased in very modern terms, okay, which is category theory. Okay, so the ideal you kill correspond to some geometry. Okay, and then the map you consider also correspond to some geometry. Okay, or not? Maybe you just look at this example, these exercise. Maybe you look very plain. Let me see. Maybe you just look at this. So many x number on it. Actually, they are geometry that you are killing here. And they are geometry that you are killing inside here. Actually, this assignment here can be phrased in geometry term. Okay, but now you only first learn algebra, so you see it as an algebra. Okay, actually, this whole assignment is like a geometry, in particular the first one. Okay, we are doing geometry. So that's the reason why we have x, y, z. We have t here. X, y, z meaning 3-dimensional space. 1-dimensional space like line. Okay, CT. Polynomial ring with one variable. You should imagine you are playing with a line. Okay, 2 variable, 2-dimensional space. 3 variable, 3-dimensional space. Okay. Okay. So I have some extension requests for some of you. So do you still want to extend your assignment or not? Yes or you okay? How about the other? Extend or don't extend? You can complete. How about the other? Well, if we getting there, complete or you guys, what's your opinion? You have to extend or don't? Ah, uh, the other side, extension. If no need, then I only grant some. Yeah, you need some extension. Okay. So if you need extension, you message me. I only grant personal extension then. I don't need to grant public extension. Okay. If you need extension, you just talk to me. Okay. Yeah, because I haven't finished marking your assignment for, so I think we don't have time to discuss. So I plan to do a revision class. You guys want to come or not on revision week? Any one of you interested? Can I have see the rest of hand how many of you interested to do revision class in during the study week? Can you show? Can? Okay, I think more than half, so we can do it. So you want to do physical or online? Online. How about the others? Physical or online? Online. Everyone online. Any physical sound or not? I'm not suppressing. Huh? What do you are physical? Only one. So I think I need at least half to do physical, then only we make it physical. Otherwise, only one physical, then everyone online. Anyone want physical? Okay, see raise of hand if you want. Only one. So we do online. It's okay. Okay. So where's the day? Study week, which day? Which day? Quick, decide. Day or what? After you do revision, then you come ask question. I'm not giving you any, don't expect extra hint. You have to bring your question here. Ask question. What you don't understand, what you don't know how to do. Okay. I'm not like the other teacher. Don't expect me to do that. Okay. So which day? So you want to do revision first and then you bring all the question coming. So maybe choose Wednesday, Thursday, Friday or that. Right. Friday? Friday? Okay. Friday what? Morning, afternoon? Afternoon. So how many hours? 1 hour, 2 hours? I think 2 hours. Yesterday we already go about 2 hours. So 2 to 4? 2 to 4. Friday 2 to 4, study week. Okay, so you please bring question, ask about the concept or some technique you don't know how to compute. Okay, bring those questions. So we'll meet on team. Okay, Friday 2 to 4. Okay, and then I will make announcement also. Then I should, by that time I should return all your assignment. Okay, maybe we should take a break here because I want to go into new stuff. So so exam content, I think we'll just stop at a product ring. Okay. And then starting from the group correspondence theorem, because last midterm we didn't really have tests on correspondence theorem, not either uh, in what is that? Uh, assignment. Only after midterm we do correspondence theorem. So that will be in the exam. Okay. Yeah.
For the LCM stuff.
LCM, maybe not so. No, I think no, not included. I guess.
So the things before our lecture 14 is just correspondence theorem that part.
Yeah. I think basically you can use assignment to judge what I test. So it's the assignment after the meet. Or the assignment after the meet. So my testing criteria is I will pick something from the assignment, okay, and then pick something that I mentioned in the lecture. Last time I know what do you mean? What do you mean? I'm not sure. I cannot confirm. But because last assignment, those questions are quite standard. So I'm not sure if this time is standard for you. Yeah. Because last time we had review question, right? Yeah. This time don't have review question. And then okay, this time there's no help for you. You need to understand all the definition and theorems. No help. No definition sheets. Okay, no theorem sheets. You cannot bring chit chat.
Not equivalent stuff. Yet the stuff you apply only.
No, no. You need to understand. If not, you have to derive it on the spot. Okay. Yeah. So you see, throughout this course, we have been talking about isomorphism. Okay, so you definitely need to know how to show something is subjective, something is subjective, how to show something is a homomorphism. How many types of homomorphism? Group homomorphism, ring homomorphism. Okay. All these you need to know how to show. This is a very important concept. Yeah. Show that something is the same. Similar to first isomorphism theorem, you want to identify the quotient. Yeah. So this is the concept that run through this course. You definitely need to know how to show. So you can tell your friend if they want the assignment extension, they should message me. Okay, email me. And then for the rest, if you can manage it, please send it on time. And then I should start my marking on time. So because last time it was some of you that hand in lab, partially also because of my own family issue. So everything clashed together. So I don't have much time. Okay, hopefully, but before next Friday or Wednesday, I should give back to you. Hopefully. Everything. Okay. Okay, so let's take a break until 9:02. Okay, I'll take attendance before we resume. Venus. Oh, here. Blood here. 伟泽。Yeah. 大能。天。天科。天科。泽瑞。Not here. Steven. Helen. 石宇。Helen. Ying Seng. Not here. 林。Yeah. 海伦。Yes. 金波。Yeah. 华英。Yeah. P. Sean. Yeah. 一起 yes 可以 yeah 雪岩 yeah 家燕 OK 李凯人家 OK 文硕 yes 一定 yeah 玉维 yeah 烟火看了烟火陈燕喂陈燕啊 yeah sick no no Okay. 林金 okay. 董洁 yeah. 宜州柳青 yeah. 登城周宁古力 yeah. 子谦德轩 yeah. 莹莹 okay. Grace yeah. 沙耶嘉文明修 okay. Michelle yeah. Ryan Eddie 雪梅 okay. 子源 okay. yeah.
你看，讲到我们现在都可以，就 OK 了，这个变 I， 这个变 I。
Oh, yeah. Oh, okay. Yeah.
这其实这样，
看看啊。什么问题都有。哦，我看看，你怎样找到你的？你用的 fact that 音可以否在 coefficient 就把它拿出去。Yeah， 也可以问，
也可以。
可以问，先给我。Yeah。
Okay, everyone ready? Okay, so I cannot change your study method a lot now. But what I want to say is different teacher have different practice, at least here, not so consistent. Because I like to give a hard assignment. So I also welcome you to come and find me during my office hour. So I make myself available, okay, after class. It's not like the other teacher, because maybe the other teacher doesn't like to see you after class. So they make it easy in their content. So you don't need to see them. You can do it yourself. Okay. So I do a different practice. So if I make it so hard and then you make yourself very hard, then you will experience bad feeling. Okay. So maybe I feel sorry about it, but one thing I can help is you can kind of search for me. Okay, whenever you need help. Okay. But what I want to say is the learning path is always hard. If it's not hard, then I think you are not learning properly. Okay? Yeah. So for me, it's a if then segment. If you don't learn it hard, then you don't learn it well. Okay, continue. So I want to continue with this fraction part. You can relax a bit if you want. Just listen. What's the story going on? Okay, and then try to think about why I do this. So fraction. What is fractions? I think you know fraction pretty well. Okay, so the slogan here is the fraction field of Z is the rational number. Okay, so note that I put field here. So meaning, if I take this fraction of something, it should be a field. So what's the field difference between field and ring? All the non-zero multiplicative elements are inputable. Okay. So how do we introduce a fraction field in Z actually? So you will see that actually 1/2 equals to 2/4. Why so? Why so? Because we will define the equivalent classes A over B equals to C over D if AD equals to BC. Okay? Note that we introduce it as AD equals to BC. We don't say there's a factor we cancel out. Not like that. Okay? It's because if we cross multiply, they are the same. Okay? So this is an equivalent effect to what you have done before, cancelling out the factor. Correct? Not? Okay, why 1/2 equals to 2/4? Because if I cross multiply, 1 times 4 equals to 2 times 2. Okay, no? We don't like cancelling out stuff because we don't always can always cancel factor. But we can always multiply. Okay, so that's how we change the language. Okay, we change the language. So how do we add? Okay, what's the addition in fraction? Okay, what's the multiplication in fraction? Okay, how do I add? A over B plus C over D is what? AD plus BC over BD. And then AB times C over D equals to 1. AC over BD. Okay? But this definition makes sense. Okay, this definition makes sense because we just multiply number together and then we put them either above the line or below the fraction line. Okay. But you remember in fraction, we don't want to divide by 0. Okay, we don't want to divide by 0. So we don't want the denominator to be 0 here. Okay, but could it be the case that B don't equal 0, D don't equal 0, but BD equals to 0? Could this happen or not? Do you think this will happen? Huh? No. In any ring, cannot happen. You sure? Consider Z4. Consider Z4. What's the thing non-zero multiply together, you get 0? 2. 2 times 2 becomes 0 in Z4. Okay or not? Okay, in Z, surely you won't have this happen. But if I change my ring, okay, in Z4, could this happen or not? Could this happen in general or not? It can, in Z4. 2 is not 0 in Z4. But 2 times 2, you get 0 in Z4. Understand or not? Okay, so that's why I said max is very flexible. You think that the rule is that, but if you change to different space, it works. Okay, this is the real part of max. This is the real meat of max. Max explore all possibilities. Okay, if you just learn max by heart, by way, by calculation, then you lose most of the max fun. Okay, yeah. So this is why we're gonna introduce this, what we call an integral domain. So what is an integral domain? So the integral domain, okay, R, or sometimes we call a domain just a domain, is a ring. Okay, first of all, it's a ring with the following property. Okay, first of all, we don't want it to be a zero ring. Okay, it must be something non-trivial. Okay, this is not a zero ring. Okay, and if A and B in R, okay, if A and B in R, and AB equals 0, then one of them must be 0. Okay, then one of them must be 0. One of them must be 0. Okay, cannot be both non-zero then multiply to 0. If two things multiply to 0, one of them must be 0. Then this is what we call an integral domain. So this integral domain has nothing to do with the calculus integral. This integral refers to the integer. Okay, so sometimes you see integral in max. Sometimes it refer to integer. Sometimes refer to the max integration. Okay, yeah. So last semester I teach you this, right? So this semester I teach you the other one, integral domain. A b equals 0, A equals 0, or B equals 0. Okay. So we have seen integral domain before. For example, what? For example, Z. Z. And ZX, polynomial ring over Z. These are all integral domain. Okay. Okay. And your favorite R also integral domain. Complex number also. So if you take them and then build your polynomial ring, it's also integral domain. Okay. Okay, so you've seen a lot of example of integral domain. Non-example. How about non-example? Just now I give you Z4. Okay. If Z4 is non-integral domain, then the polynomial ring is also not. Exponential ring is also not integral domain, because Z4 will behave as a constant polynomial then. Okay. Any question about integral domain? Okay. Okay. What else? So next, last time I promised you this definition, right? So what's this definition here? An integral domain in which every ideal is principal is called a principal ideal domain. Okay, so last time we talked about some ring that has ideal only principal. Okay, so what is that? So what is the principal ideal domain? PID. So sometimes we write it as PID. Okay, last time we talked about we have Z. Right. So every ideal is generic. Every subgroup is cyclic, for example. But ideal is also principal ideal. Generated by what? Generated by the GCD among the number inside that. Correct? Not? All the ideal in Z is generated by the GCD of the number inside the ideal. Okay. And then who else is principal? Whose the ideal is principal always? For example, what? A polynomial ring over a field. Okay, it's generated by what? It's always generated by the unique monic polynomial with the smallest degree n, positive degree n. Okay, so these are the results we have established before. Now we are just collecting the result, collecting the example. Okay, if you're not familiar, you should go back and look again. Every ideal in the polynomial ring over field is generated by one polynomial, which is the unique monic polynomial of positive. This is what you use to show some of the question in the assignment. Okay. Next. So next proposition. So any subring of a field is an integral domain. Okay, every subring in a field is an integral domain. Is this easy to see or not? Any subring of a field is an integral domain. In other words, all the fields are integral domain. Okay, is this easy to see? Suppose AB equals to 0. Okay. You want to show that A equals 0 or B equals 0. So how to show it? Inverse, right? Because in the so in the field, every non-zero element has an inverse. If either A or B is 0, then you are done. Right? Suppose A not 0. Okay, so let me write here. If A is 0 or B equals 0, then we are done. So suppose A not 0 now. Then A inverse exists. So I can multiply A inverse on both sides. And then I prove that B must be 0. Okay. Okay. So to show integral domain, if A B equals 0, A must be 0 or B must be 0. Okay. So I show that suppose AB is 0. If one of them is 0, then we are done. Okay. Suppose both of them are not 0 now. Okay. Suppose both of them are not 0 now. Then I can simply multiply by A inverse on both sides. Okay. And then I show that B is 0, which is a contradiction. Okay. Yeah. Okay. So I'll keep going. Proposition. If R is a domain, then the polynomial ring Rx is also a domain. Okay, it's also a domain. Okay. Is it obvious or not? Because this x here, I don't have any relation on it. It's just some intermediate variable. Okay. So I attach more things to R. And then this x shouldn't have interaction with R. This x is just an intermediate, a variable. Okay. And then within x itself, it doesn't square to 0 because I don't have relation here. I don't Q by some function. Okay. So it should be a domain as well. Okay. Okay. Next. Feel free to stop me if you like. Don't just let me go. Okay, next. An element alpha of a ring is called a zero divisor. Okay. What does a zero divisor mean? So from these two words, right, can you guess or not? Zero divisor. Meaning what? You can divide 0. Normally when you divide 0, you get what? Or divide by 0 is undefined, right? If you go and divide the 0, you should get 0. But this zero divisor divides something non-trivial for you. Okay, so what does this mean? So something is called a zero divisor if, first of all, it is non-zero. Okay, we don't want 0 to be a zero divisor. And if there exists another non-zero element B such that Okay, let's write this alpha as A. A, B equals to 0. Okay? Or in other words, is what? 0 over A equals to B, which is non-zero. Okay, so this is just a side note. We don't want to write divide because we don't always invertible. Okay, we don't always invert the element. But what we can do is we consider the multiplicative form. Okay. So for example, just now, in Z4, who is the zero divisor? 2. Okay, 2 is a zero divisor. Okay, because there's two non-zero element multiplied together, you get 0. So meaning what? If A is a zero divisor, B should be also a zero divisor. Automatically satisfy this definition. Okay, so if you have two non-zero things multiplied together, you get 0. You are called a zero divisor. Yeah. All the non-zero thing in the field is a zero divisor. No, right? Go and look for real number. Real is a field. Real number is a field. What's the two non-zero thing multiplied to get 0? Nothing, right? Unless one of them must be 0. This Z4 is special because it's a modular arithmetic. Z3 is a field. Can you find zero divisor there? Z3 maybe not. How about Z5? Okay, I didn't know. Maybe. Yeah. Yeah, Z6. But that one is not a field anymore. It's not prime. Z6. It's not a field. Okay. Yeah, we can try. Yeah. Yeah, field doesn't have a zero divisor. Correct. Or in other words, it's an integral domain. Okay, so proposition here. So this lead to this proposition. So an integral domain is a non-zero ring which contains non-zero divisor. Okay, I think this proposition is pretty straightforward because zero divisor is tailor-made for things that A equals 0 implies that A equals 0 or B equals 0. Because if you take the contrapositive, you should get the zero divisor definition falling out. Is this obvious or not, this proposition here? Yeah. Which direction? Say again. So if there's no zero divisor means what? There's nothing that so for every non-zero element, you multiply to the element, you won't get 0. Yeah. So this is the equal segment. Okay, need to prove. So if it is an integral domain, means what? If A, B equals 0, then A equals 0 or B equals 0. Okay. Suppose there's a zero divisor. Then they have two non-zero that multiply to 0. Contradict, it is an integral domain. Okay. Yeah. And just now we discussed with Ziqian, if there's no zero divisor, then there's no non-zero element that multiply to all the non-zero elements to get 0. Okay, so the only way you get 0 is you need to multiply by 0. solve if you need. Okay. Okay, so what's so nice about this? Okay, it's because we want to do the cancellation of factor. Okay, if that is the cancellation law. Okay, why you can do so many cancellation of factor, cancellation law here? Because of the cancellation law, because of the integral domain you have. So let B be an integral domain. Okay, and then you take 3 elements in your ring, in your integral domain. Suppose that AB equals to AC and A not 0. Okay, A not 0. Then B equals to C. Okay, can you think for a moment how to prove this? Can you think for a moment how to prove this? So in previous your practice, right? If you see A, you cancel A on both sides. Okay, why can you do that? And why can you do that? Sorry? So how to use that? Yeah, how to use that? How to prove it now? Yeah, eating. Sorry? Why not BC on both sides? Why not BC on both sides? Okay, so let me try. So you start with this. Then you minus BC on both sides. Like this. AC on both sides. Okay, yeah, sure. So minus AC on both sides. This is allowed in ring. So you get AB minus AC equals to 0. Minus AC means what? You add by the inverse of AC. Right. So what's next? Sorry. You can distribute the A out. And then because you are an integral domain, two things multiply to 0, meaning A must be 0 or B minus C must be 0. But you are told that A is not 0. So B minus C must be 0. Since R is an integral domain and A not 0, B minus C must be 0, which implies that B equals to C. Okay, so you see, we abstract the idea of cancellation factor into an integral domain. Okay, all the integral domain I can do the same thing, cancelling the factor because of the property of integral domain. Okay, you can see that we don't just cancel, we do some distributivity law, and then use the integral domain property. Does it make sense? Any question about this proof? This proof is very short and straightforward. You should get it on the spot. Okay, this is the expectation we have. Okay. What we have used, we only use inverse. Okay, we use the additive inverse. We have used distributivity. We use the definition of integral domain. That's all. Okay, there's no special treatment here, construction. Okay. Any question about the proof? Any question about the proof? Is it straightforward? Okay, some of you okay. The other, is this straightforward? How to do a survey? I need to tell you my expectation. You need to tell me your experience. Then we will try and tailor some practical expectation. Okay. So Xuan, what do you think? Okay, you think okay. Okay. Okay, good. Okay. Next. So definition. So let R be a ring. So we define what the fraction is. Okay, so what's the fraction? So fraction is really just a symbol. Okay, it's just a symbol. A over B or like this. Okay. Elements of R. And B is not 0. Where I lose something. So here where A and B are elements of R. Okay. Okay. So this is fraction. So how do we regard the element in R as a fraction? Can we regard every element in R as a fraction? Can you guess? What's the fraction for R? Every element in the ring is a fraction or not? Can you guess? Yeah, see. Yes, R over 1. R over the multiplicative identity. Okay. So it depends on your ring now, right? In your assignment 4, there's a special ring about set, right? So you can form a fraction there. Okay, you can form a fraction there. It's just a symbol, right? These A and B might not be number anymore. They might be set, or they might be something else. It's just a fraction. Next definition. So how do we define two fraction is the same? Okay, so this is exactly how we defined last time. I mean, in the motivation just now. If I want to say that A1 over B1 is the same as A2 over B2, or they are equivalent, okay, and we write A1 over B1 equals to A2 equals to B2, if we only know ring operation, we only know how to multiply, we only know how to add. Okay, so if what? If the cross multiplication are equal, A1 B2 equals to A2 B1. Okay. We only know how to multiply in the ring. Okay, so we just check. Is it A1 times the other denominator is the same as the A2 times the other denominator? Okay. Yeah. To be precise, we can define this fraction is a symbol A over B, right? We can define the A to be the numerator, B to be the denominator. Okay. But it still doesn't make sense, right? Because our ring will be different ring, not numbers, but set and so on. Function, even function. Okay, function. Actually, you have seen fraction of function before, right? F over G. Right? Yeah. Okay, so it's just a symbol. So we're going to define what is a fraction field of a ring. So now we're going to define fraction field of a ring. So the ring we only work with is the integral domain, okay? Or we should put integral domain. Okay, we don't want to divide by something 0. Okay, we want to avoid that. So we only work with the integral domain ring. So let F be the set of equivalent classes of fractions of elements. Okay, so when I talk about this, you should imagine typical example, rational. Okay, rational. What is in the equivalent class of 1 over 2? 2 over 4, 3 over 6, 100 over 50. Sorry, 50 over 100. Okay. Yeah. And so on. Okay. 3 over 6, sorry. Right. So they live in the same equivalent class. Okay. Of an integral domain. Okay. So our claim is once you have this, they form a fraction field. Okay, they form a fraction field. So to talk about fraction field, right? Talk about field. What do you need to tell me? Or a ring. What do you need to tell me? How to define a ring? How to define a ring? You need what? A set of elements with what? With two LOC, addition and multiplication. Okay, so you need to define that. If you tell me something is a field, please define the two LOC for me. Okay, so one of them, you need to define the sum and the product of two fractions. So how do we define it? We define it exactly what you have done in the high school for your rational number. What is A over B plus C over D? We need to make the denominator the same. AD plus BC. And how to define multiplication? So we just multiply the numerator together and the denominator together. So here's B. Okay? Okay or not? Okay, yeah. Okay, so this is how we define. And then second, you will see that the integral domain automatically can be seen as a subring of the new field we built. Right? So what's the rule here? I send A to A over 1. Okay. I think the first time I learned rational number, first time when I learned rational number, I think I'm not sure you. Did you ever ask how to write 2 in terms of sum A over B? Never asked. You won't ask me. Because when you write out the rational number, right, you see like 3 over 4, 5 over 1, right? Never ask what is 5 over 1. Never ask what is 7 over 1. Never ask. Did you ask your teacher what is 7 over 1? So when my teacher tell me everything over 1 is the thing at the top. And this is what we learn here. So R and embed as a subring into the fraction field. Okay. A equals to A over 1. Okay. Yeah. Okay. And then next is a bit technical. So this is a mapping property. So in case if R is embedded as a subring of another field, then let's say my ring embedded in another field. So what can you think about this? So we have Z, right? Embed in rational number. It also embed in real, right? Okay, so what can we do with this? So we can set a rule. So the rule A over B equals to AB inverse. Okay, AB inverse here makes sense now, right? Because A is a thing in the ring, B is a thing in the ring as well. Okay, but we embed AB into the field. Every non-zero element in the field is invertible. So B inverse exists. So I can write like this now. exists in the field. Okay, exists in the field. So for example, 1/2. 2 in the Z is not invertible. But if I embed 2 into rational, it's invertible. What's the inverse of 2? 1/2. Okay, so the inverse exists in the field. So I can write B inverse. So this rule here will embed the field F into a larger field F prime 2. Okay, so in other words, what? In other words, the injective ring homomorphism P from R to F prime can be extended to another injective homomorphism phi from F by the rule phi of A over B by the little phi A and phi little b inverse. Okay, so let me draw this diagram for you. So I have a R. Okay, first of all, I have a R. And then I have a map into F prime using this little phi. And then I have a map from where? Let me see here. So I have another embedding. Let's call it F prime to F. Let's see which one is F, which one is F prime. So let me see here. Did I copy something wrong or not? Let me see. Okay, I think I'm right. So this is phi, this is F prime, and then I can extend this map to this injective map, which we call it big phi. Okay, so meaning what? If you have a ring homomorphism from R to any other field, you will pass through this fraction field. You will pass through the fraction field. So the fraction field construction is the smallest field that contain R. Okay, so the construction we have just now, we just consider symbol, okay, A over B, and then consider the equivalent classes. Okay, and then I tell you how to add. I tell you how to multiply. Go and find all the identity, and then show that it is what? Associative, commutative, what else? Distributive, right? Okay, and then this is the smallest field you get for your integral domain. I guess this is the last property here. If you have any other map, you can extend from the map that map R to the smallest fraction field. Okay, so the fraction field we have is the smallest field that contains the integral domain. Okay, so the smallest field that contains Z is Q. Okay, so it's Q, it's rational. And then you can go from rational to other field. Okay, no? Yeah. Yeah. So field extension topic is covered in Galois theory. Okay, AN2, if you are still interested. Okay, maybe we won't prove this because we don't have much time. And let me give you some example then. For example, okay, we've met this, so rational number is a fraction field. That. Okay. And then last time we have defined the fraction field for polynomial ring, which is R bracket round bracket X. Okay, this is a fraction field of R adjoint X. And remember last time how we defined this? How we define this? I just tell you that invert all the non-zero element in Rx. This R bracket X has all the inverse from the R adjoint X. Okay. So in this language here, we will call this Rx to be the field of a rational function. Okay, we will call this a field in a rational function. And then what is this? So by the definition just now, these are equivalent classes of fractions over G, where F and G live in R adjoint X, and G cannot be 0. Okay. So what's the things in here? What can you find here? For example, you can find 1 over X. Right. For example, you can find 1 over X inside here. For example, you can find 1 over X squared inside here. You invert all the polynomial. You can find 1 over X squared plus 3 inside here, for example. I invert every polynomial. Non-zero polynomial. Okay? Okay. Okay. Any other question about assignment or about the lecture content before? Before we finish? There's an office hour if you come later. Not to come later. Any question? No. So you can if you already start doing revision, or you try tutorial question, or you want to discuss some assignment question, maybe you can bring on Friday as well. Yeah. So Friday I want to talk a little bit about maximum ideal, prime ideal, and then modules. Okay. Yeah. Sorry. Galois theory. You want to hear about Galois theory? If you want, then I can put some in. Oh, okay. Sure. We can preview some advanced algebra course that related to this class. Okay, so that you don't feel like alone. I'm just doing this ideal sharing those. Right. Okay, you want to help about our theory, maybe good sum in. But for me, I want to relate to a module. Because module is quite common in mathematical research now. Yeah. Any last question, Ziqian? No? All right. If not, see you on Friday.